So now we start with Taylor's theory from the technical point of view after studying examples and motivations. So I have to introduce a very standard issue and notation that is related to the notion of subsequent derivative or repeated derivatives. We start with an abuse of notation to which you are already used, but I have to make it clearer. So we have a function f from the open interval ab to r, of course, with real values. And this function is differentiable in the whole interval ab. Then it is possible to define the function f prime from the open interval ab to r that associates to every x the derivative of f prime, at the point x. This is an abuse of notation because here f prime, as introduced up to now, is just the numerical value of the derivative at a given point x. But it was introduced in such a way it is already a function as a notation. So now we extract just the symbol f prime to denote a function. So f prime, without argument, is called the derivative function of f. But function sometimes is omitted for brevity, so I will just say the derivative of f. Perhaps I already said the derivative of f. Yeah, this is the notation that we use. Now, so the remark. Since we introduced f prime as a function, it may be possible to differentiate further f prime. In such a way, we find f second, which is nothing but the derivative of f prime, f third, which is the derivative of f second, and in general the notation is f, then a small bracket at the top of the f, and inside the bracket we put the number of differentiation that we made in order to obtain the function, so fm. Okay, this is just a notation. Let me just give an example. Very stupid example, but to fix the idea, so if f of x is x to the power 5, then we have f prime of x is 5, x to the fourth power, f second of x is 5 times 4, so 20, x to the third power, and so on and so on. At f fifth power of x is simply the factorial of 5, which is 120, and then fm is equal to 0 as a function whenever m is at least 6. Okay, so by the way, you notice, you already knew, but I have to tell you, you notice that the derivative of a polynomial, so the iterated derivative of the polynomial ends up with 0 when we differentiate a number that is strictly larger than the degree of the polynomial. So this is an important remark. So let P be a polynomial of degree m then P is differentiable infinitely many times. What does it mean? Of course, nobody differentiates a function infinitely many times. You don't have the time to differentiate it infinitely many times. But it means that whatever is a natural number m, then the mth, I already used m, whatever is n, a natural number, the nth derivative of m exists. As a function. Moreover, Pn is a polynomial of degree m minus n if n is not larger than m. In particular, it is a constant if n is equal to m. And 0 if n is larger than m. So it is elementary, but I had to tell this, and still more important is another notation. One says that f is of class CK and write f belongs to the set CK of AB if f is differentiable k times, so there exists k, f prime, f second, up to f kth in the interval, in the whole interval AB, and the functions f prime, f second, f third, up to f kth are continuous at all points, at every point, let me say, at every point of the interval AB. It may seem that it is not necessary to specify that the function and the derivatives are continuous because they are further differentiable. F prime must be continuous in order to have f2, and so on and so on. But this is not true for the kth derivative. Since we do not specify anything about the subsequent derivative fk plus 1, then fk is not obliged to be continuous. Then when I write here that all these functions are continuous at every point of AB, the additional information exists and concerns the function fk. Okay? And when I use this notation, ck of AB, or when I say that f is of class ck, What I mean is that all derivatives, especially the case, in particular the case, are continuous. Okay? So ck of AB is the set of all function f AB to R such that, and here I can simply copy what I wrote here, and paste. Such that f is differentiable k times in the interval AB and the function are continuous at every point of AB. Okay. So the symbol ck of AB really denotes a set. And you have to know this, okay? So let us go now with the technical part of Taylor's theory. And I will give you first what I would like to call the fundamental lemma of Taylor's theory. The lemma may sound somewhat technical or abstract, but you will see that from this lemma, then Taylor's formula comes really in a very natural way. So this is the statement of the lemma. Let capital R from AB to R be m times differentiable and in particular f belongs to the set Cm of AB. Okay? And let x bar be an internal point of AB. Since AB is open, every point is internal. Then R is little o of x minus x bar to the power m for x going to x bar if and only if R of x bar is equal to R prime of x bar equal to R second of x bar. So every derivative up to the mth computed at x bar is 0. This is extremely strong as a statement. Let me try to understand what happens. What does it mean? So with pictures. First, consider here the point x bar. What does it mean that f of x bar is equal to 0? It means that the function f crosses, the graph of the function f crosses the origin, the point 0, 0. Mm-hmm. Now, second, if I have f of x bar, and moreover, and here we have that f of x bar is little o of 1 as x goes to x bar. Another picture, which is quite informative to this respect can be the following. Consider here x bar, and now ask yourself, what does this hypothesis f of x bar equal to f prime of x bar equal to 0. So what you have in mind here is probably the parabola. And here, this is the parabola, not very symmetric. And here what you have is that f of x bar is lido of x minus x bar. You see here we have that the function and the derivative are 0, so the function is lido of x minus x bar, but we can go for the simplest function that is, oh sorry, I want it to be red. The simplest function here that has f of x bar equal to f prime of x bar equal to f second of x bar is equal to 0. For instance, the cubic function, which is this one here, and for instance, x minus x bar to the cube. And here you have that f of x is lido of x minus x bar to the square. So you see, at every step, when you impose a further derivative to be 0 at x bar, then you find that the function is closer and closer to the x-axis, near to x bar. The contact is stricter, okay? So this is exactly the point when you says f of x bar is equal to f prime of x bar equal to all derivatives up to the mth equal to 0. Here, what you find is that the function is really very adherent is very, 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 very close to the x-axis. And here you have f of x is lido of x minus x bar to the n. So you see that there is always this correspondence between the minimal number of derivatives that vanish at the point and then the order of the infinitesimal here. And so let us prove it. Let us prove this fact. So it is a double implication. So we start first from saying that R is lido, and then we prove that all derivatives are 0. Or better, no, we start from the other, from the second. Probably it is more natural. Proof. So let us start from the inverse. We suppose our hypothesis let me write like that. The j's derivative at x bar of r is equal to 0 for every j between 1 and m, then r is little o of x minus x bar to the mth power for x going to x bar. So what we have to prove that r of x divided by x minus x bar to the m goes to 0 as x goes to x bar. So, of course, it is an indeterminacy indeterminate case of the type 0 over 0. Then we try to apply the L'Hopital. So we consider r prime of x divided x minus x bar to the power m minus 1 times m. So the derivative. It is again of the form 0 over 0. Then we consider the derivative r second of x divided by m minus 1, x minus x bar divided by m minus 2. And it is again 0 over 0, and so on, up to r to the m power, the mth derivative of r, divided by the m derivative of x minus x bar to the m, and we know that this is r, mth derivative computed in x, divided by m factorial. And this goes to 0 as x going to x bar, since Rm is continuous and Rm of x bar is equal to 0 by hypothesis. So now we apply the first theorem of de L'Hopital, or the second would play the game. So applying de L'Hopital back, we obtain r m minus 1 of x divided by m factorial x minus x bar goes to 0 as x goes to x bar, and backwards, and iterating backwards, we find r of x divided by x minus x bar to the power m goes to 0 as x goes to x bar. This is a very important conclusion, and this proves the theorem in the inverse implication. Now we go to the direct implication and we see what happens. So the proof of this part is complete. Now we move forward and we assume that R is little of x minus x bar to the mth power as x goes to x bar. And what we want to prove is that Rj of x bar is equal to 0 for every j from 1 up to n. Okay? And okay. So let us go by contradiction. There exists, we assume that there exists a k in the set 1m such that rk or 0n such that rk of this is 0 here, rk of x bar is not 0. Okay. Then let us compute this limit. The limit for x going to x bar, for instance, from the right, of r of x divided by x minus x bar to the m. This is equal to 0 by hypothesis, since r is little o of x minus x bar to the n. On the other hand, you have that r of x divided by x minus x bar to the m can be written as r of x divided by x minus x bar to the power k times 1 divided x minus x bar to the power m minus k. Now, 1 over x minus x bar to the power m minus k, for x going to x bar from the right, goes to plus infinity as x goes to x bar from the right if m is larger than k, so if k is less than m. And it goes to 1 as x goes to x bar from the right if k is equal to m. Okay. Now, Consider the other factor, r divided by x minus x bar to the k. So r of x divided by x minus x bar to the k is of the form, again, 0 over 0. So after differentiating, so this is to the k, sorry, differentiating k times the numerator and denominator so finding at every step always an indeterminate form of the type 0 over 0, so we differentiated k times. We found at every step an indeterminate form of the type 0 over 0. We end up with rk of x divided by k factorial. This goes to rk of x bar divided by k factorial. Then going backwards by the L'Hopital up to the k times, we conclude r of x divided by x minus x bar to the power k goes to rk of x bar divided by k factorial, which is different from 0. Therefore, going back to asterisk, we have r of x divided by x minus x bar to the m goes to plus infinity as x goes to x bar from the right if k is less than m, and rk of x bar divided by the factorial of k, again as x goes to x bar from the left if k is equal to m. And by hypothesis, the hypothesis formulated for contradicting the thesis, by hypothesis we have that this is different from 0. So in every case, this ratio goes to something that is not 0, but this is in contradiction with our general hypothesis. So, but this contradicts 1. So, contradicts the hypothesis. That says that R is a little o of x minus x bar to the nth power for x going to x bar. Then it is not possible that rk of x bar is different from 0, and this time the proof is complete. Okay, I prefer to leave this video just for this lemma, because it is very important, and we will see in the next video how from this lemma, Taylor's formula that provides us exactly what we are looking for, namely the best polynomial approximation to a given function around a given point x bar. So we will see how this Taylor's formula immediately emerges from this lemma.